Hello, everyone, and welcome to our high performance memory Ask Me Anything. I'm Tim Messagey, and I am joined by a panel of Rambus memory rock stars, starting with Frank Farrow, who is our Senior Director of Product Management for Interface IP, John Ebley, VP of Marketing for Memory Interface Chips, and Steve Wu, who's a Rambus Fellow and Distinguished Inventor at Rambus Labs. Gentlemen, thank you. Thank you very much for joining me. This is for me the equivalent of a Beatles reunion, and I think we're going to have a great time. So before we get started, I want to let the audience know there's a couple of ways you can ask a question. One is we are going to have pop-ups that our production team will push to your screen from time to time that you can use. You can also go to the navigation that's on the left-hand side, and if you click on Schedule and find the High Performance Memory AMA, there's a link for Ask a Question. Click on that link. You'll be able to insert your question, but you'll also see what other people have asked, and you'll have the opportunity to upvote on those questions if you're so inclined. I'm just going to take the top questions from that queue. So what is popular for you all, I will ask of our panelists, and I will direct the questions. But panelists, if you feel like a colleague has something that you think they'd like to add, or maybe they're better to tackle that question, feel free to pass the ball. This is Team AMA. One wins, we all win. We're going to get through this together. So thank you again for joining us. We've already got a lot of questions in the queue, so why don't we go ahead and get started. John, the top one is about DDR5, and I suspect you are best suited for that one. It talks about the lifetime, the rich lifetime DDR5 has ahead. Can you talk about some of the technologies that were implemented in DDR5 to extend that useful life, and how long do you think that will be?
Okay, thank you, Tim. I'm under a lot of pressure now that I need to give a rock star answer, but I'll do my best. Yeah, so if we look at DDR5, it's a technology that's been designed and conceived to last at least a decade. We've seen DDR4 be dominant for quite a while. So yeah, let me take you through just a few things. I think the simplest thing that happens when we move to a new DDR technology is you update the addressing, right? You want to be able to have enough address bits to have these high density components. DDR4 sort of topped out at 16 gigabits. The addressing has been extended to allow DDR5 to go up to 64 gigabits.
Okay.
In order to achieve the density increases within that DRAM itself, we need to make some changes so the DRAM companies can make these devices. I think the most important thing was the introduction of on-chip ECC. What this should allow the DRAM companies to continue to scale their technology node, to continue to put more capacitors and bits on a given size of silicon. The other feature to sort of allow this scaling more in the bandwidth direction is increasing the burst length from 8 clock cycles to 16 clock cycles. That allows the DRAM to be designed in a way that the row activation time doesn't have to get faster by another factor of 2, because that's kind of a hard limit, especially as you keep increasing the density. Now, once you increase the burst length, you need to make some other changes, which have some good side effects, because every time you do an access, you want to get back a cache line, because that's sort of the communication mechanism between the CPU and the memory. So what we've seen with the DDR5 modules is we go to a dual channel architecture. So there's 2 independent controls of the command and address. Each of those will return 40 bits back. The reason why that's 40 bits is because you'll get 32 bits of data. 32 times 16 bursts will give you 64 bytes. We needed an additional at least 8 bits to get the reliability that we see. We always want to have single error correct, or I'm sorry, yeah, single error correct, dual error detect. And you need probably about 6 bits for that 32, and then a couple extra bits just to round it up to the nearest version of factor 4. The other nice thing of having that dual channel per module is that does give the CPU more parallel resources that it can use. So it's going to be more efficient using the memory, and it should help to reduce the loaded latency of the system. So those are all great things. Now, as you increase bandwidth, you need to think about efficiency, because you need to manage the power within a power envelope. So the voltage has been reduced from 1.2 to 1.1 volt to allow for that efficiency. There have been new chips introduced, like the SPD hub and the thermal sensor, to enable faster communication at boot time and polling. And these also give more temperature telemetry so that the server can be smarter about managing its overall thermal envelope. And then just a couple more. I think in the signal integrity gets harder and harder as we go to these higher speeds. So DDR5 introduces decision feedback equalization. It introduces a lot of mechanisms to train not only the DFE, but the timing of the interface. So ways to accelerate that, features and say the RCD, the DB, the DRAM. And then very tight limits on clock delay on the chips, as well as jitter. And then finally, we've had to really think about how do we test these components, how do we test the module? The old ways of looking at an eye diagram and making sure it's open so high and open so wide doesn't work at these really high speeds. You really need to move to more a statistical BER approach. So there's been a lot of work done within the DDR5 spec to lay the groundwork for that, and that will really scale well into the future. So those are all the things that I think have been put into DDR5 to make sure it can last.
Right.
DDR5 is going to come out of the gate at a very impressive speed bump from 3200 to 4800. That's about a 50% increase. Some of the efficiencies I've talked about should make that performance advantage be even higher. Micron had a nice public study where they did some simulations and saw that it could be as much as 87% increase.
You pick up because of higher efficiency.
Because of the higher
with doubling the data rate, but you're getting 87% performance bump.
Right,
well, that's huge. That's huge.
And so I think this is all laying the groundwork for DDR5 to really be the dominant memory technology for servers and desktops, through the end of the decade.
Right.
So I think that's the answer, or that's my opinion.
That's a great answer. And John, typically the new standards launch at kind of the, maybe you get the efficiency bump, but if you top out at 1600, then the next standard takes it up at 1600, right? So this is kind of new with DDR5 to launch at this higher data rate. How high is it spec'd? What data rate can it go to?
Yeah, it looks like it's spec'd to about 8,400 megatransfers per second. I think there's been some discussion about maybe 8,800. So it's going to be somewhere in that kind of, I'd say, high 8,000 megatransfer per second range.
Wow. Okay.
So almost a tripling of, say, the 3,200 where
exactly
more leaves off. So yeah, I think it's an impressive technology.
Lots more bandwidth, lots more efficiency, and Steve, I've got a question about AI training that's kind of similar, thrust. It talks about how can we keep doing what we're doing as AI training growth sustainable. I remember some of the articles that you and Frank had talked about or had written for publications a couple years ago, where we said, hey, we could get to 100 billion parameters, and a year beyond that, maybe 1 trillion parameters. And when we wrote that, I was almost like, is that really legit? I mean, 1 trillion parameters? Now that's where we're at. We're at 1 trillion and headed higher. how do we continue to sustain that? And how big a issue is memory bandwidth and performance a part of sustaining that?
Yeah, that's a great question, Tim. It's really interesting. It's obvious that no exponential can go on forever, but
Right.
calling the end of it is very, very hard.
Right.
People are very clever, and they'll come up with very interesting ways to stay on those trajectories if they can. What we've seen is that people are doing really the most that they possibly can within an individual engine. And the way they've continued to improve the performance is they've tied multiple engines together. And so that parallelism of the engines allows us to continue having much larger models, and it allows us to train these much larger models in a more efficient way. So if you think about kind of what the impact is to memory and interconnects, there's really two parts to that. One is you just need more capacity to store these larger models. Like you mentioned, the size of these models are growing at about a factor of 10 every year. And that's just faster than any other technology growth rate that's really out there. So we do the best we can with the individual components, and then we tie as many of them together in parallel as we can.
Mm-hmm.
Now, the other part of that is, okay, once you get to the kind of capacities that you need, then you need to have some way to kind of move the data quickly. So people are, by nature kind of impatient, and they'd like things to happen as quickly as they can. So this much larger amount of data now has to be moved much more quickly to allow you to get an answer in a reasonable amount of time. And that's where you start to see pressure on things like, memory interfaces and links. And we've seen tremendous growth in the rate of data transfer for all memories. So if you look at HBM and GDDR, which are typically used in AI, the growth rate of the data there, the life cycles of those parts are much shorter in part because of the demand of markets like AI. So every few years, we're on to the next generation of part that tries to double the performance. And the same thing with links. We see kind of an acceleration of the standards for PCI Express, kind of the dominant chip-to-chip type interconnect, but other types of custom interconnects as well that are really ramping up the speeds there. So, really we're seeing that capacity is very important, and that data movement both between chips and from a chip to memory, those are really becoming the bigger bottlenecks, and you're seeing the industry respond with faster innovation.
Mm-hmm. Mm-hmm. Hey, I've got a question on GDDR6 and HBM3. Frank, can you talk about, what your recommendation would be if a customer was designing where you should use which of those memories, and kind of what's the state of the art relative to both GDDR6 and HBM3?
Sure. Yeah, we view GDDR6 and HBM3 kind of solving kind of two different types of problems, right? So it really comes down to the application and the specific bandwidth requirements of a given customer. If you look at GDDR6, it's a more traditional DRAM in the sense that you put it down on the PCB. Now you're running very high speed signals, right? GDDR6 today runs 16 to 18 gigabits. There was just an announcement last week, or it might even this week, from one of the DRAM vendors going up to 24 gigabits. So when you're designing boards for GDDR, you have to certainly be very conscious of how to route those signals, especially going up to 24 gig. So there's certain special care taken, and there's an expense associated with that. But if you look at HBM, then you have a kind of different set of physical design problems. And we'll talk more about that. But with HBM, you have a 2.5D kind of structure. You have a 3D DRAM, and so you're stacking things. So there's HBM is going to give you much higher bandwidth. You're going to be going significantly faster, but you've got an expense. So what we see is that customers are trading off. GDDR gives you relative to HBM, you're going to have a more cost-efficient system, but as you move into HBM, it's going to be more expensive. So HBM gives you higher bandwidth, better power performance in a much smaller footprint, but you're going to pay for that. So that's the trade-off. So for example, if I need 1 terabyte of performance, I'm probably going to wind up with HBM. because you can put down one HBM and you'll have plenty of bandwidth. But GDDR, in that case, you'd have to put down several GDDRs, and you're running all these pins at high speeds. It's going to be more complicated physical design. So again, I think they're very complementary in the sense that we're seeing GDDR for bandwidths in the up to about half a terabyte would be a good solution for GDDR.
And Frank, as you see AI ML continue to proliferate, are you seeing more HBM applications to the edge as you see GDDR move to the endpoints?
Yeah, there's not a clean answer there. It's kind of interesting because some of the earlier applications we had for HBM, believe it or not, were actually in 5G edge systems. If you look at the base station, they're starting to look like little data centers.
Right.
And so HBM was being used there for a number of things, for lookups, for buffering, and it looked like a good solution. So yeah, it's expensive, but if you're doing an AI accelerator card, then GDDR might be a better option at the edge of the network. So we're seeing both HBM and GDDR being used in the edge, and again, it's very heavily application driven. We see, as you're doing more inline processing at the edge of the network, the amount of space you have on the board for memory is starting to get tight, and so you really need something like a GDDR where you're running 16 plus gig. Can help reduce the amount of DRAM down the board, but you don't have to go all the way to spend on HBM. So it's like I said, it's not a simple answer. It really looks at how much processing you need, how much expense you can deal with, and then also what's the end application that you're trying to achieve from
right. And AI/ML, Steve's kind of this bifurcated application because you have both training and inference. But as you go to more heterogeneous computing, do you expect to see more specialization in memories or more unification of memory? Steve, that was for you.
Sorry. Yeah. It's a great question. What we've historically seen happen is that, when a market is starting, it'll try and use the best fit memory that it possibly can, and they'll try and bin it. So what we saw in mobile was standard kind of, SDR and DDR DRAMs were initially used in those phones.
That's right.
And what they would do is they would bin them, and they would pick kind of the lowest power components. And then eventually the market got big enough that it warranted its own specific design. And so I anticipate the same kind of thing happening here where, as the market starts to specialize a little bit, what you'll try and do is you'll try and leverage the technology that's out there. But then over time, if those markets get big enough, and if they can kind of warrant, their own designs and the economics work out, then sure, you'll start to see more differentiation and potentially even a new kind of memory. One area that's really been quite exciting is watching AI, just the adoption of it and the growth. And, AI has really been a driver for some of the high-end memories. And it's not unreasonable to think that some of those memories may, have their own offshoots or may start to incorporate very specific, functions just for AI.
Great. And John, how there's a question about higher data rates stretching out the adoption cycle because of an increased complexity, and it's one of those that we've talked about. The need is going up at an accelerating rate, but the adoption cycle is taking longer because of the complexity. How do we square those two issues?
Yeah, so I think higher memory rates and a new memory technology can contribute to that, but I don't think it's the cause of increased adoption cycles by itself.
Right.
Our systems and processors aren't sort of forward compatible, right? You can't take an existing system and just plug DDR5 in it. There's the processor, the server needs to be designed with that new technology in mind. Now, at the same time that new technology is being introduced, there are other new technologies.
Right. So
Right.
we do the try to lift all
Yes.
sides of the board at
Right,
the same
right.
time.
So,
Right.
you want more cores, you want more security features, you want new instructions and features like for AI, ML. You want the latest PCIe, latest and greatest. You want CXL. So you're trying to bundle out of these technologies and go. And I think the secret is you do not want to be the long pole. So the bear is chasing all these people, and you want the other guy to get eaten. So I think within the memory ecosystem, we put in a lot of upfront work to sort of grease those skids, right?
Yes.
We get our components early and test them. We work with our DRAM customers to get modules and test them either on ATE or maybe like an early version of the platform. And we want the memory to be ready to go when everything else is ready to go. Now, even once everything's ready to go, the end customer still has to do their own testing.
Exactly.
And I mentioned a little earlier, I think a long time ago, you probably could have put the memory in, run a margin test, look at the result and go yes or no. Everything today is statistical, right? So there needs to be a certain number of systems, a certain amount of time tested, the analysis. So definitely there's not only the development and getting all the components and technology ready, but then there's that sort of back end of, okay, now I have my particular system, I need to go run through all my checks. So yeah, I think managing that's difficult. It's just, we're going to have to keep backing up and being ready. For instance, right, we made an announcement, last October about our second generation RCD running at 5,600 megatransfer.
Exactly. Yeah.
So we have a part, it's ready, it's in production, but we quite haven't seen the launch of, we haven't seen the official launch of, I would say, the Gen 1, server speeds.
Exactly.
So we're staying ahead to make sure we're not the long poles.
and clearly with DDR5, there's going to be 3, 4, 5 waves that are going to take us through that, kind of decadal lifetime. Right. Okay. Right. Yeah.
I mean, the first jump was 800, will it continue to be 800 every time? Maybe. We saw some weird things with DDR4, and I think it'll continue to be that way because it's really about the memory solving the problem, that the system guys and the processor guys are trying to solve. So we're flexible. We're ready to work with them to make their products and dreams possible.
Right. And Frank, do you feel like you got more degrees of freedom when you're talking? I mean, when you're talking a main memory solution like John's talking about, there's basically the whole platform. But if you do an AI accelerator, do you have a little more freedom in that you don't have to kind of uplift the entire platform in order to upgrade to kind of the next generation memory for an accelerator versus the main processor?
Right. Yeah. I mean, typically those accelerators will go through something like a PCI interface. So then the memory itself is kind of hidden behind that in this case. So we see a lot of these AI accelerator cards in different variants and flavors. So for example, you may have a 250 watt AI card that you could really put a lot of, you can put some HBMs on that, and you've got plenty of power, and you could put a pretty heavy duty processor on that. You may have other 75 watt cards that you've got to really balance your performance. And so these will accelerate, AI training, for example. But then you've got the other, AI cards where you're doing AI inference. And so those cards are going to be, much more cost sensitive. They're probably power sensitive and not have as much performance. So yeah, so those definitely, within those cards themselves, you can pretty much do whatever you want as you're talking to the system from a memory, because that's behind it. And I think,
Yeah.
And so, we'll probably, there may be a question on, CXL memory. That's something that'll probably come up. So
Right.
I won't jump ahead yet.
Thank you. That'll get my wires crossed. Okay, great. So we are seeing pretty rapid evolution for the HBM standard, and we moved from HBM 2E, 2 to 2E to 3. Pretty rapid progression. And what did we have to do? Because we've got a question here, kind of like, what's different between HBM3 and HBM2E that really allowed us to take that kind of next big jump in terms of bandwidth performance?
That's right. So the actual bandwidth change is HBM2E topped out at 3.6 gigabits per second per pin, and then as we move to HBM3, we're up at 6.4 gigabits per pin. So you've got almost a 2x jump in terms of performance. But then in order to allow that jump, there's a couple of things that they kept the wide interface. So HBM3, right. HBM2, you still have that 1024-bit interface. Again, you're trying to continue that concept of going very wide and slow to keep the power profile under control. But now with HBM3, you're getting up into the, it's anticipated that the spec will continue to go faster. There's been announcements by some vendors to, now they can go up to 7.2 and it's anticipated to go faster. So in order to keep the power down, they have reduced the IO voltages. And so you're down at, 0.4 volts on the IO. So that's, again, trying to keep, so we're actually going faster, but we're staying within the same power profile, which is nice. They also increased the number of channels. And as you're doing different applications for AI, you have the ability to get better granularity on your DRAM access now. So one of the things is DRAM efficiency. How well are you utilizing the DRAM? So with the additional channels, you could you can manage those word sizes much better.
Okay.
So those are some of the things that I'm trying to think if I missed. Those are some of the big changes. They went from HBM2E to HBM3. So again, trying to keep the power down a little bit better on the efficiency, and of course, getting the speed up.
Okay. Very good. Steve, on this one's about heterogeneous computing, and you talked about that in the keynote this morning. And as we are in the accelerator age, what if those accelerators are FPGAs? Does that play part of this, this heterogeneous computing? And will we see more high performance memory interfaces on FPGAs?
Yeah, that's a really good observation. And yeah, FPGAs have really always had a part in the data center, and they've been adopted at various levels by different players. And so, Microsoft was very public with their work on Catapult and using FPGAs to improve search. And so, one of the really nice things about an FPGA, as you know, is you get a highly configurable engine. And so as a computing paradigm starts to evolve very quickly, you don't have to worry about that overhead of spinning an ASIC and getting it right. You can just come up with a new bit file and you can adapt much more quickly. And so that's really one of the benefits that you see with FPGAs, is that ability to adapt. And the other thing that goes on in these data centers is that the workloads that are being run, they vary much more now. And so being able to tailor a bit file to specific workload needs and change them out very quickly, and that kind of plays to the benefits of an FPGA. I think another thing is that FPGAs are great for rapid prototyping. So if you're not exactly sure, what the right way is to do something, you can do a lot of experiments, and then when you're ready, you can turn that into an ASIC. Now, the challenge of a lot of this is that these architectures are shifting to be much more data aware. So they have to process the data more quickly, and they have to move it more quickly to other engines in the system. And what that means is that the FPGAs themselves, because they're becoming more integral to the rest of the system, they've got to actually have faster interfaces on them. So faster memory, so that you can really make use of what you're doing on the FPGA. All the logic that you're putting on there has to be usable. And then you've got to get the data on and off to the next stage of the pipeline, or the next element that has to work on your results. And so faster kind of chip-to-chip interconnects are going to be very important as well. So yeah, they're basically a first-class citizen now in these heterogeneous computing systems, and because of that, they have to have the same kind of support and infrastructure as all the other first-class citizens that they coexist with.
Right. And I think, Frank, someone was very inspired by what you were talking about. We have a question on CXL. Frank, why don't I just, if you'd start, because I'm sure we've all got, perhaps except for me, have a viewpoint that we want to bring to the panel on CXL. The question is, what can CXL bring for memory for AI/ML?
Right. Yeah, I kick it off. I think this is an area where where Steve has spent a lot more time, and maybe John, thinking about it. But I think the idea here is, how can we use CXL to start to pool memory resources in an efficient way that allows us to let kind of real time adopt different memory configurations in a way that's this way we don't have we don't have wasted memory. How can we kind of keep that utilization up, and by having these kind of memories that you can access in real time for different compute loads, can go and put different attached to different CXL memory configurations. So that's really the essence of that. And I know Steve's done some research there, so he probably can go into it much deeper than I can.
Yeah, I think that's the things you mentioned, Frank, are really some of the big attractions. The things that we've talked about how the data set sizes are growing. It's one of those things where they're really exceeding the size of direct attach, like DIMM modules or something like that. So having the capability like CXL, where you can add additional memory beyond the traditional direct connect sockets, that's definitely a big plus. The other thing that CXL brings is it brings a coherence now. That allows you to really make sure that when multiple engines are sharing that data, that it's kept coherent. And why that's important is that one way that when you have a big problem and you break it up among multiple engines, one way you like to work on those problems is you like to have one engine do some work and produce a result, and you like to have the next engine take that result and do further processing. So the coherence now allows you to communicate through the memory itself. You're not necessarily sending explicit messages back and forth. Instead, you're just signaling when you're done with the data, and then the result data from one engine is then consumed by another engine. And the coherence makes it much, much easier from a programmer's standpoint, and making things easier to program just enables the technology to proliferate. So that's it. Those are some of the really big things that CXL brings to the table.
Steve, does that memory coherence, does that positively impact not having to move the data as much, and the energy benefit of not moving the data?
Yeah, really, there are cases where the data has to move no matter what. But what's hard as a programmer is coordinating that movement. What's a lot easier as a programmer is to simply access the data and let the underlying hardware take care of the movement for you. So it's very easy as a programmer to kind of mess up when you're explicitly trying to move the data back and forth. But if you simply think of it as reading and writing from addresses in memory and letting the underlying hardware take care of everything, that's a programming model that everyone's familiar with, just reading and writing data. But the beauty of it is the hardware underneath takes care of its movement back and forth, and ensuring that that those engines are seeing the correct value of the data, and the programmer doesn't have to think about it.
Great. Hey, one of the technologies that we all love is DRAM technology, but as the process nodes get smaller and smaller, and the number of electrons we can actually store on those capacitors gets smaller and smaller, are there other memory technologies out there that are showing promise as a DRAM substitute? I think that's the nature of this question. Will DRAM be replaced in the future by universal memory?
Yeah,
Steve, you want to start with that one?
Yeah, I can start with my thoughts on it. So, there's over really the last 30 years, there's been a lot of work on different types of technologies with the hopes of maybe getting to a point where they might replace DRAM technology. And I'll say a couple of things here. So, the industry, I think, is doing a good job to look into lots of different alternatives. But one of the things that we've repeatedly seen is that if you kind of think about what's really great about DRAM, there's about 10 or 12 kind of parameters that just work out really well for DRAM. So, for example, it's got a very, very high endurance. So, it effectively looks infinite. It's got a very low read latency and a very low write latency as well. The power looks pretty good. And when you take a look at other technologies, like, there's a lot of effort to put, say, flash as potentially an augmentation or maybe even replace some of the DIMM sockets. And when you look at flash, you look at it and you say, well, it's got some great properties, right? Mm-hmm. It's non-volatile, which means you don't have to refresh it. It's got very high density. It's got low cost per bit. So those things are all great. But, for many of these technologies, there's just one or two parameters, like in the case of flash, the write power is enormous, right? And there's an endurance issue as well. So for many of these kinds of memories, there's one or two of these critical parameters that just are so bad compared to DRAM, it effectively takes you out of the game. It could never be considered a replacement. And so unfortunately, for a lot of the kinds of memories that people have been proposing so far, they look great on a lot of these parameters, but there's one or two that just don't fit well at all with the existing kind of use cases and kind of performance models. So, the industry will continue to work, and but for right now, I don't see anything that's going to cause, say, a large fraction of the DRAM, bit cells to move over to some other type of technology. I don't see anything certainly in the next 5 years, and it's going to be beyond that for something to really take its place.
Right. Which reminds me, I had this question for John about DDR5. Steve's talking about DRAM having to meet a lot of different parameters, and DDR5, had to deliver more bandwidth, higher data rate, but it had to stay within some envelopes. John, is that correct? I mean, you had to stay within the power envelope. You had to stay within a reliability envelope, if you will. And you mentioned the temperature sensor and the SPD hub. How did those kind of help with remaining within that envelopes that we had to address for DDR5 outside of the obvious benefits of higher bandwidth and higher speed?
Good question. I think the main benefit from from an efficiency or staying within the envelope is that the SPD hub has an internal temperature sensor. Right. The DIMM has two other temperature sensors that are connected via an I3C bus, which has been an upgrade from what we saw in DDR4. The I2C bus runs at about 1 megahertz, whereas I3C runs 10 times that speed. For things like polling or at initialization time, when the link's not up and you can't do in-band transactions, that really helps manage the time and the ability of data that you can get, sort of that real-time sensing. So you're going to really have in these DDR5 systems a fine grain, view of the temperature within the server. Right? You're going to have 3 data points per DIMM that's populated. And then the server can use that information to do several things, right? It can manage fan speed. So you're balancing sort of noise and energy consumption versus increasing heat flow or increasing airflow to remove the heat. If it is getting hot, you can change the DRAM refresh rate to make sure that the reliability stays constant. And if either of those tricks don't work, then you can always choose to throttle back the bandwidth. That's sort of a last resort. Yeah, so I think the bus speed improvement, the SPD hub itself is a bidirectional redriver of the I3C. So it sort of hides the loads of the other target devices on the DIMM from the main bus. So that's another thing that contributes to that speed. So I think just the speed of that bus, those additional sense points, yeah, allow the system to be more intelligent about how to manage it and stay within the power envelope.
And to get that intelligence, we're adding more telemetry, we're adding more sensors, if you will, and we're adding more. These are smarter DIMMs than
Yes.
in past. There's a lot more silicon there to give you more intelligence on the DIMM. That's great. We've got a question on the CXL protocol working with HBM3, and I think we could extend that question to CXL protocol working with any of the memories. But Frank, do you want to talk about how CXL can work with HBM3? Go ahead.
Yeah.
Go ahead.
Yeah, I was just going to say, yeah. I mean, what you have behind the six, I think is the point, right? You're kind of we could theoretically have GDDR6 behind it. You could have HBM. Right. I mean, all these are DRAMs, right? And even the question, kind of Steve was alluding to the fact that, you know, when we can get back to the storage class memories, but you know, the question around why are there different types of memory? If you really look, these are all fundamentally DRAM technologies, right? So HBM is taking DDR technology and stacking it in a 3D way, so you can kind of get very wide access. And GDDR was designed specifically originally for the graphics application, right? So you could have, again, DDR memory, but you can, with graphics, you're going to have a certain kind of data, or it's going to be very repetitive, and so you can do it much faster. LPDDR, again, DRAM now with more power states behind it. So again, these are all based on the same fundamental DRAM technology. And so, yeah, so in theory, you could build up any type of memory system you'd like to see there. So I don't know if John or if Steve want to add to that or comment.
Yeah, I think one of the main attractions of something like CXL is that ability to abstract what's really behind, the CXL buffer and what's across the link. And so that kind of abstraction, that flexibility really allows you to tailor whatever memory it is you need to meet the needs of the system. So you can definitely envision some systems that they're going to have much higher kind of bandwidth needs, and they'll need something kind of potentially like HBM, and they may not need as much capacity as DDR, so that you can service that part of the market with that trade-off. There's going to be other systems that need to have both very high capacity and high bandwidth, and they may use something more like DDR, where you're putting a bunch of the DDR devices in parallel and kind of killing two birds with one stone to get both the capacity and the bandwidth. So it's all really, it's really another way to kind of trade off the things that each of the systems needs by giving you a nice, good interconnect that can service these different kinds of trade-offs, and you can just meet the performance and cost needs as you see fit.
Steve, CXL also has the benefit with DRAM attached to, whether it's CXL pooling or CXL expansion. As a fan of your webinars, you've talked in the past about this huge latency gap you have between direct attached memory and, SSD storage if you have to go there. Can you talk about what CXL can do to help?
Yeah, absolutely. So, if you're used to seeing these kind of memory hierarchy diagrams, people will show, when you try and access direct attached memory, there's a particular kind of latency you can get to. And then if you can't fit in your direct attached memory, your next choice is to go to the disk hierarchy. And that, something like an SSD or something like that is several orders of magnitude longer to get to, and it's a much lower bandwidth as well, just like Tim mentioned. So really what people are looking for is something to fill that gap. And what CXL offers is, although it's not direct attached in the same way as a DIMM socket is today, it's still a very low latency link. and it's a high bandwidth link. And so it's going to be much, much faster. It's going to look a lot more like direct attached memory, maybe not be quite as low latency, but it's not going to be anything like 10 or 100 times the latency. It's going to be much closer to the latency of DRAM. And then, from a bandwidth standpoint, extra pins that are, high performance serial interface type pins, you'll be able to move data very, very quickly onto the processor, much faster than you would for something like an SSD. So it's it's just kind of an extra interconnect that lets you augment the capacity and the bandwidth well beyond the direct connect interface of the DIMMs. So yeah, it's a great way to kind of fill that gap and provide you more capacity and bandwidth than you'd otherwise be able to get.
Stephen, Labs, it was a while back, but Labs did some hardware-based work on something very similar to that. And what kind of performance benefits did you see?
Yeah, I mean, we've done a few different kinds of research projects in our labs organization, looking at how memory hierarchies could evolve. And so, yeah, we took a look at things like, what happens if you did think about serial attaching memory. And so some of the things that you kind of find are that, it's not surprising. There's going to be a lot of applications that don't really see much detriment in terms of performance. They really need the capacity. And so anything you can do to avoid going to disk is a good thing. And so for those applications, the performance gain is actually there. And the actual magnitude of that gain, it depends on the specifics of what the latency and the bandwidth look like. So we've tried, we tried varying the range, and just, speaking in general terms, not surprisingly, the lower the latency and the higher the bandwidth, the more performance you got out of it. But there is a cost to actually implementing something that's very low latency and very high bandwidth. So we found across that range, you could get different kind of price performance points depending on what it is you were looking for. Okay,
very good.
And then, I
John,
think.
Go ahead, Steve.
Sorry, the one other thing I was going to add was just that, we have looked at the potential benefits of pooling in the past as well, where like if you could build a node with a lot of memory in it, we took a look at things that could, additional features that a system like that could provide to a fleet of servers, and even thinking a bit about what happens if you were to move processing off those server nodes into this box with a lot of memory. So kind of near data processing as well. So all of those things are, there are benefits for each of them, and there's just different trade-offs depending on what kind of your usage model looks like.
Right. John, I've got a question here about single-ended signaling on memory. And clearly we're single-ended for DDR5. And you talked about some of the innovations that make that possible, going up to 8.4, potentially even higher for DDR5. Do you think we're going to stay on that track, that we'll be able to continue to extend that kind of performance with single-ended architectures?
When I first joined Rambus, there was a belief that single-ended signaling couldn't go beyond 1 gigabit per second.
So, like,
I will never again.
Never say never, right?
I will never again give a limit.
Well, we made it past 1. Thank God.
I think GDDR is a great example of how far you can push, single-ended signaling. I think what I've learned along the way is, differential signaling is very noise immune, right? And it's very robust. Single-ended signaling can be just as robust if you're in a very, very low noise environment. So, a lot of what has happened, I think, along the way is people have incrementally introduced cost that then was able to sort of scale down, right? So they're board level things, they're socket level things, how you lay out the traces. Because, crosstalk, I'd say, is one of the biggest killer for single-ended signaling.
Right.
So people have looked at, ways in the system just to reduce crosstalk. Power integrity and power noise is another killer for single-ended, because that can show up as sort of, because you always have it in a single-ended system, you have a reference voltage, and how power noise injects into the signal versus the reference is quite different, so you have to manage that. So, I think we've been incrementally managing things to continue to allow it to scale. It's just, especially for server memory, where you're trying to get as much bandwidth out of each channel, it's a very efficient way to do it. It's very low latency, because you're not deserializing, you're not putting in forward error correction, you're not doing PAM4,
Right.
So yeah, I think clearly for DDR5 it'll continue to be single-ended signaling.
Absolutely.
I would guess that we would continue on that path, until it runs out of steam, or if it runs out of steam.
Yeah.
And CXL does provide this other way to connect bandwidth, right? It's sort of a interesting way to introduce differential signaling and kind of have them coexist. So
Exactly.
Yeah. And Tim, I don't know if you want, if I can add. So John, that's good. And in the case
Please, Frank.
in the case of GDDR, like you said, we're running up. We've got 18 gig going. We're working on 20 plus gig GDDR6, and these are still single-ended.
Right.
Even back in the day, Rambus had done research, showing how high we can push that single-ended systems. And so as we're moving into the next generation of GDDRs, now we're starting to do that exact same head scratch again. Are we out of single-ended yet?
Right.
And so but we're still working in single-ended. The other thing is from a system design, John kind of alluded to, from the physical design environment. If you look at HBM, you're going through an interposer, so you've got a channel that's kind of a couple of millimeters long, right? So that, of course, the silicon interposer introduces different types of characteristics from the signal. In the case of GDDR, now you're going over a board, and you could be going half inch or more. So I think and then looking at those materials that we're using, it's a combination of not just how fast the PHYs can go, but then what does that channel look like? And so managing that, so we're looking at that design based on, okay, here's what the channel requirements are, and then how does that translate back into the PHY, into the physical layer? And so those are the trade-offs we're constantly looking at for these single-ended systems. But we're certainly getting, it's going to be, I think the next round will be very interesting as we get into the next generations of GDDR.
So my takeaway is one of the big advantages of single-ended signaling is latency. And latency is really key in many of these workloads and applications. Steve, you've talked about kind of the next generation architectures that will provide a lot of benefits in terms of TCO and, composable architectures, if they're disaggregated, have many, many benefits of matching the kind of the resources to the workload. But as you disaggregate, do you take a penalty on latency, and how do you manage that?
Yeah, it's definitely the case that if you were to take all the resources you really need and put them all in one box, you can get the best kind of performance that way. The problem is that with the range of workloads people consider these days, it's never the fact that one size fits all and that you're going to use all those resources as needed. So something needs to change. And as you start to think about the data center scale, right? Being able to compose your workloads as they come in across a wide range of users and server hardware, that's looking more and more appealing. And that's kind of why everybody's looking down that path. The challenge is, how do you manage performance expectations, right? So there are going to be some users that performance is less important for. And in that particular case, really cost and the economics of how you provide them with a good solution, that's going to matter more. And so something like a composable type of infrastructure may be much more cost effective. And then you can pass that savings on to the users. For certain very high performance applications, you're going to still see people, wanting to stay a little bit more with dedicated resources if they can. And so a composable infrastructure allows a bit of that flexibility where you can have a wide range of services that are, maybe, that they're so disaggregated to the point that maybe they are not the highest performance type of infrastructure. But from a cost standpoint, they provide a superior cost and operating point. What some of the work we found is that for certain types of applications, disaggregating and kind of moving the memory in particular further away from the processor really had no effect on the performance at all. So, that's one example where, if you can maintain the same level of performance, but if you can provide a much less expensive infrastructure, then from a cost performance standpoint, that's much better. So, it's really that, managing kind of the performance expectation is it's really up to kind of how you architect the system and how you architect that composability. So I at least everything I've seen, I think it's possible, and I think things like CXL are new technologies that allow that to really be possible.
Right. Excellent. Well, gentlemen, why don't we wrap it there? It has been great playing a set with in the Beatles reunion here with my memory rock stars. There are a lot more questions left, but audience, please fear not. I know where all of these gentlemen live, and we'll make sure that all the questions we didn't have a chance to get to during the session, we will get back to you on them, or we'll post the answers on the forum so people can see those. We've got additional sessions that are coming up, including a roundtable where we're going to talk about the future of the data center, and Steve and John will reprise their roles and join us for that. Frank has been an absolute hero. He's done 3 sessions today. Those will all be available for on-demand replay. This and Frank's sessions will be available for on-demand replay. And John has a session on DDR5 coming up. Steve's keynote from this morning will obviously also be available for on demand. If you have questions after this session, please feel free to use the same idea. Go to the session, go to the schedule, select the session, go to ask a question, and we'll make sure those questions get to these gentlemen. So I want to thank John, Frank, and Steve for this. Ask Me Anything for high performance memory. It's been great. And to our audience, thank you all for attending. And I hope you have a great rest of Rambus Design Summit 2022.
Thank you, Tim. Thanks, everybody.
Thanks, everyone.